Hello, I'm Peter, and in this presentation, I will be covering our paper, Marking Material Interactions with Computer Vision. This work was done in collaboration with Sandra, Ruhan Yang, and Ellen Du from the University of Colorado Boulder, as well as Clement Zheng from the National University of Singapore. As researchers and educators in the field of tangible user interfaces, we are tasked with both designing interactive systems as well as mentoring other designers. Building these interfaces requires physical computing, which is largely driven by off-the-shelf electronics. Designers benefit in their efforts from the widespread accessibility of MCU platforms such as the Arduino and Raspberry Pi, but despite their widespread use, researchers have noted several challenges with this electronics-based physical computing approach. Notably, creating physical circuits can be an intimidating task for anyone who hasn't encountered electronic components before. Additionally, debugging circuits can be quite tricky since problems in the flow of current cannot be perceived without additional tools. Based on our previous work with CV markers, we realized that they could function as an alternative to electronics for physical computing. With just a single camera, multiple interactions can be detected without the need for any circuitry. For our pictorial on the printed paper markers project, we explored a range of interfaces all mediated by CV markers and paper structures, but that was just the work of a relatively small design team. We have continued to develop this CV marker-driven approach and shared it with other designers. In this paper, we reflect on our work with computer vision markers as a material for physical computing, as well as the results from a series of studios in which we shared this technique with other design students. To that end, we developed Beholder, a web-based programming library that leverages CV markers as a material for detecting tangible interaction. In this presentation, we will introduce the portfolio and the studios in which the portfolio projects were created. We then discuss the key insights that emerge from reflecting on this collection of work. And through these insights, we point towards the strengths and constraints of using computer vision for physical computing. The portfolio that we assembled includes 15 projects that were produced from 2020 to 2022. This work was done across 3 design studios conducted at the National University of Singapore and at the Atlas Institute in CU Boulder. As mentioned before, to support the easy use of computer vision in these studios, we developed a front-end web library called Beholder. This library wraps a JavaScript implementation of the ARUCO fiducial marker detection algorithm. These markers are easily printed on paper, which designers can then stick onto their constructions to track interaction. Once detected, the markers offer a range of values that can be used to sense interaction, including presence, position, rotation, and a unique ID for each marker. The first studio, titled DIY CV Interfaces, was an 11-week design studio class with 21 undergraduate industrial design students. In this studio, students were challenged to develop DIY computer interfaces for everyday activities anchored on the themes of work, learn, and play. This brief was provoked by the fragility of the global supply network highlighted by the COVID-19 pandemic, which increased interest in DIY activities. We saw a diverse set of topics from the 7 projects produced in the studio. For example, one group created ARU controls, a tool to map marker interactions to keyboard output on a computer to support custom DIY interfaces. And another group created Hexbox, a cardboard game controller kit with swappable bespoke inputs. With Studio 2, titled TinyCade, we wanted to focus more on play as the context for tangible interaction. We also set out to explore smartphones as an all-in-one computational device. With these specific goals in mind, we organized this studio to run within our own research groups with designers who were already familiar with Beholder. The designers in this studio created TinyCade, a DIY platform inspired by arcade machines from the 1980s that exclusively features the use of commonplace materials like cardboard and toothpicks. From this platform, 3 games and 1 educational kit were developed, each with their own bespoke controller. The TinyCade platform itself features 2 mirrors on the inside, which enable the phone to function as both a display and a detection device. Our final studio, CV Games, was a 13-week design studio with 15 undergraduate industrial design students. This studio was inspired by TinyCade as well as the many game-based projects from Studio 1. In this studio, designers were challenged to develop a new DIY video game platform for a specific audience. In total, 6 games were produced, though for 2 of these projects, the designers opted to use a different technique than CV markers. Some of the games produced here include Cade Cafe, a game platform that facilitates full-body interaction with markers that can be attached with Velcro to a felt suit, or ARU Scan, a toy which enables caregivers to map CV markers to specific images and sound files for kids to find and scan. We collected all of the work produced from these studios into our portfolio for reflection. Through our reflections, we examined a couple of key themes. How did designers use CV markers to detect physical interactions, and what physical mechanisms did they construct to facilitate their use of markers? We also asked, how does the practice of physical computing with CV markers compare to that of electronics, and how did designers understand the mechanics of building physical interfaces with CV markers? We also wanted to surface what interface materiality CV markers facilitate. Our first insight centers around how CV markers mark identity and interaction constraints. With electronics, designers will often use a different component to sense each different interaction. For example, buttons for presses and a potentiometer for turning. However, with CV markers, a single component is capable of sensing a wide range of interactions. For example, the simplest value a marker provides is presence, and it was used in a variety of ways. Presence can be disrupted momentarily to detect a passing obstruction, such as in the coin counting mechanism in Fun Fun, or used to indicate a certain state, as with the D-pad in the Light Cycles game for TinyCade. We've collected and categorized all of the techniques designers used across these projects into this set of examples. Important to most of these is how designers can identify distinct but similar interactions simply through the unique ID of each marker. Our second reflection was on how CV markers mark interaction events in the physical world. For example, a marker can continuously report on the position of a slider by looking at a marker's position in the detection feed, such as with the claw controller, but they can also be used to mark an event in interaction space. For example, track features a row of individual markers, and when each one is revealed to the camera, the designer knows that a certain threshold has been passed. We view this use of markers as a kind of programming in the physical world. Instead of using a series of if statements in code, the designers of track placed markers where they wanted events to occur and responded to the marker's presence accordingly. We also observed a method of debugging CV markers with human vision. When working with electronics, there isn't really a sense that humans have that can detect the flow of electricity. But with CV markers, people can easily identify if a marker should be visible to the camera, and can then determine if the bug is in their interface or the detection side without checking the computer. This leads us to the materiality of physical computing with CV markers. The markers themselves are usually made of paper, but any high contrast rendering will do. They are also essentially tied to immaterials like light, camera space, and environmental conditions. CV markers can be coupled with a huge range of materials. In our studios, we saw paper, cardboard, wood, and acrylic, but other materials are certainly possible. TinyCade in particular made use of cardboard since during the height of COVID isolation, the designers had an abundance of shipping boxes lying around. This materiality also points to some of the limitations of CV markers. Lighting must be consistent for the detection to work, and a low-resolution camera feed reduces reliability. To this end, camera motion blur can also pose a challenge, especially on computational limited devices like smartphones. When working with CV markers, we are also constrained to sensing only, so you will still need electronics for actuation. To wrap up this presentation, in this annotated folio, we presented 15 projects that used a CV marker-based approach for physical computing. Through reflecting on these projects, we uncovered the following insights about designing with CV markers. They can be applied to physical materials to sense a wide range of interactions. They can be used to directly mark interaction events, enabling designers to program system logic in the physical world. They can be debugged using human vision, thus enabling designers to draw connections between what they see and what a CV system sees. And they can enable designers to leverage a diverse materiality, including democratic physical materials such as cardboard and paper. We will continue to explore the techniques described in this paper, and we hope that this work will contribute to the range of alternatives that designers can employ for physical computing, and inspire more research in this area. Thank you. And if you are curious about the portfolio or the library we developed, they are available at these links.